Alright, calculus. In this video, I wanted to go over the Why So series quiz, some of the questions that you might see. So I took the quiz and I pulled up the questions here that I'm going to help work out with you so that when you see the similar questions on the quiz or the final exam that you know what to expect and know what to do for each type. So the questions that you get will probably be different because they're pulled from a question bank. Some of them are randomly generated. And you'll see them in a different order, but you'll still see similar types of questions. So one type of question is this first one, which asks if a series is going to converge conditionally or converge absolutely, or if it's going to diverge. And so you should be using the alternate series test for this, and that's found in the classwork series 2, I think. And here we have an alternating series. We can tell we have an alternating series because we see the -1 raised to the end. That tells us that the signs are going to flip-flop. So we have to use the alternating series test, which says that the limit of the sequence without the -1 should be going towards 0, and that each term gets successively smaller and smaller the further we go. But on this one, you can see that our sequence here is sine of n, and sine of n just oscillates back and forth, going between -1 and 1. So as n goes to infinity, sine of n does not tend towards 0, so this one is going to diverge. So again, when you see this conditional absolute diverging, you're going to be using the alternate series test, and you have to check to see if the sequence is going towards 0. You have to see if the original sequence, without the -1, it's going to converge absolutely. If it would converge, whether or not it alternates without the -1. So that's how you know if it converges absolutely. So for example, if you had something like the series of, let's say, 1 over n squared, and then you had a -1 up here, going from 1 to infinity, this would converge absolutely, because even without the -1, if it was just 1 over n squared, it would still converge. Whereas the sequence from n equals 1 to infinity of something like -1 to the n over just n, this would converge conditionally, because without the -1, you would have 1 over n, and that would be the harmonic series. The harmonic series is a p series, but p is less than or equal to 1, so it's going to diverge. And so this would converge conditionally because it's alternating, and 1 over n tends towards 0, and each term gets smaller and smaller as n gets bigger. So again, for number 1, use the alternating series test. Let's go on to the next question. Question number 2, I ask you to find the sum of a series. Now, usually it's very difficult to find the actual sum of a series. We don't have too many formulas, but we do have a formula for geometric series. And so you should realize that this is an infinite series, but this is actually a geometric series in disguise. We can rewrite this, and you could pull out the 5, and you can think of this as 1/4 to the n minus 1, and n is going from 1 to infinity, and this is a geometric. The 5 out here is going to be your first term, so that would be like your a sub 1, and this 1/4, that is the ratio of the geometric series. So you have a formula for the sum of a geometric series. We did this back at the beginning when we were introducing series and geometric series, and the formula for a geometric series for an infinite one, for the infinite sum, is a sub 1, the first term, divided by 1 minus r, and so here we're going to put in 5 at the top, 1 minus let's see, 1/4 on the bottom. And I typed this in the calculator before. We have to round it to 3 decimal places. It comes out to 6.666 repeating. So 6.667 is what we would type in here. So again, this is a geometric series. That's the only one that you can really find the sum of easily, and that's our answer for that one. You have to use the formula for the sum of an infinite geometric series. Question number 3 says find a power series for this function. So we want to rewrite this function. We can find a power series if we can get in the form of 1 minus 1 over some r. some ratio. So we want to rewrite this guy so it looks like this. And we can figure out what r is. And then it will be in the form of a geometric series. And we can write a power series for it. So we're going to take our original, which is 3 over 1 plus 2 to the x squared. And let's divide everything on the top and the bottom by 3. So that leaves us with 1 over 1/3 plus 2x squared over 3. And then we do a little manipulation on the bottom. We still have 1 on the top. And let's write a 1 minus 1 plus 1/3 plus 2x squared. This is a little trick, so that makes it a little bit easier to do the calculation. So I didn't really change anything. All I did was add 1 and subtract 1. But these two things we're going to combine. So negative 1 plus 1/3 we can write as 1 minus, negative 1 is negative 3 over 3. So that's going to be negative 2/3 plus 2x squared over 3. And now we want to, that's going to be our ratio, but we need to pull out the negative sign. So we're going to pull out a negative from that, like so, and we got 2/3, and then this is going to be minus 2x squared over 3. So this is going to be our r, our ratio, and now we can write it as a power series as n goes from 0 to infinity. As long as our ratio is between negative 1 and 1, this is going to converge, and we would have 2/3 minus 2x squared over 3. All of that raised to the n. Which one of these is the same as that? It would have to be the first one here. So that is this one. Okay, number 4. We have the limit as, it says x, but this really should be n here. I'm going to have to change that. As n goes to infinity of the nth root of the absolute value of a to the n equals 1. This is using the root test, and the root test, if it's equal to 1, you can look up in your notes that the test is going to be inconclusive. So that is the best answer for number 4. For number 5, we have that some sequence is going to be greater than or equal to 4/3 raised to the n, which is greater than or equal to 0, or greater than 0, for n that is greater than or equal to 1. And then what does this tell us about this? We're using the direct comparison test. So this series, or this, if we did this series of going from n equals 1 to infinity of just 4/3 raised to the n. This series is a geometric series, but it's going to diverge because our ratio is bigger than 1. So this geometric series is going to diverge. So now we know that this series, or this sequence, is always bigger than this sequence, which is geometric. And so that means that if it's always bigger and this one's going to diverge, then the one that's bigger also has to diverge as well. So this series is going to diverge. So that's the correct answer. And actually, I throw it in the word subverges, but that's not an actual word that we've gone over. So if you ever see the series subverges, you know that that's not going to be the answer. That's just to check to see if you know what the words mean. We've only used the words diverges and converges, or the test is inconclusive. So the test is not inconclusive. It would be inconclusive if it was the other way, and this series was less than. Number 6, we're estimating sine of 1.71 pi using a Taylor polynomial about x equals pi. What is the least degree of the polynomial that assures an error smaller than 0.001? All right, so if you look up the Taylor series polynomials, we did this for sine, we did it for e to the x, we did it for natural log as well. The only ones that I'm throwing on this quiz and on the final exam are going to be sine and cosine and e to the x, so that it makes it easy to find m and manipulate it. So with sine and cosine, the value of m is just going to be 1. Remember, m is like the maximum value. So if you look at the formula, All right, it comes from this page from Taylor series where we had the Taylor theorem with a remainder and we did some calculations. So this is similar to 23 and 24 using either sine or cosine. So what we want to do here is take the difference between the x and where it's centered. So in this case, we're estimating 1.71 pi, and it's centered around pi. So we take that, we subtract them. We're going to raise that to the n plus 1 power. Of course, we're taking the absolute value too, so we always want that to be positive. And then we're going to divide that by n plus 1 factorial. And then our m here is always going to be 1 for sine or cosine. For e to the x, when you get those, you're going to have to figure out, e to whichever number is higher, whether it's where it's centered or the number that's given to you. You're going to raise e to that power for the e to the x ones. But for sine and cosine, m is just going to be 1. So we want to see when is this going to be less than 0.001. And I showed you that you can do this in Desmos. You can type this into Desmos. We can simplify the top, subtract those. We're just going to have 0.71 pi over, if you type it in Desmos, you probably want to use x plus 1. And if you type it in Desmos, you'll need to have parentheses around the exponent. And then we have x plus 1 factorial on the bottom. And then 0.001 like that. Okay, here you can see I have it typed in Desmos. And we have these bands that are shaded that are in the negatives. But we're looking for the first smallest positive number. So we want to go over here. And you can zoom in here. We want the first positive integer that is after this line here. So our answer is going to be 9. So make sure you're paying attention. Do the subtraction. And this, 0.001, that could change. Sometimes it might be 0.01. Sometimes it might be 0.0001. So make sure you're paying attention to that. So the answer here to this one, again, is 9. So after you got it set up, you can use Desmos to help you solve the inequality. Number 7, determine if the series is a geometric series, a p-series, or neither. So you had a whole bunch of these on the geometric p-series test. So I threw another one on here. You're going to see it again. How do we know the difference? Well, a geometric series means that we have a ratio, and then our variable is going to be the exponent, or the exponent is a variable. And it's a p-series if we have a variable raised to a power. Okay, so this is a p-series. All right, whereas, and because p is going to be the power here, and a geometric series is going to be like 1 over r raised to the x. This is more like a geometric series where x is the variable. So p is a number, r is a number. P-series, geometric series, which one do we have here? Well, we can rewrite this as 1 over n to the 2/3. Changing the radical notation here to exponential notation. This is a p-series. P-series are going to converge when p is greater than 1. Geometric series are going to converge when the ratio is between -1 and 1. So that's how you can tell. And of course, if it's neither of those, then you're going to select neither. And I'm going to give you easy ones to figure out if it's going to converge or diverge if it's neither. So this is a p-series. And since p here is 2/3, that's less than 1, this is a p-series that is going to diverge. So number 7, p-series diverges. Number 8, this is probably one of you, this looks like it's a Maclaurin series, but this is also a geometric series. So I didn't remember which one this was, but I just thought of this as, this looks like negative x to the n. Because we got -1 to the n, we got x to the n, and this kind of looks like a geometric series where r, the ratio, is equal to -x. And it's an infinite geometric, so remember that this is going to converge, and it's going to converge to 1 over 1 minus r. So the best answer here is 1 minus a -x is going to be 1 plus x. Number 8, just one that you have memorized. You should get that quickly. It's 1 over 1 plus x. And I did it also by thinking of it as a geometric series where the ratio is negative x. Okay, number 9. What is the coefficient of the term containing x minus 3 squared in the Taylor polynomial centered at x equals 3? So again, this is going to be on the Taylor series worksheet. We did several of these. If we want to find the x minus 3 to the second power, you look at the power here. That's going to tell you which, how many derivatives we need to take. To get to the second power here, that means we need to take the second derivative. All right, so here's the formula from the worksheet on Taylor series. And notice that we want to find this term right here. So that means we got to find the second derivative divided by 2 factorial. So we go ahead and we don't have to find all the terms. I'm just asking you for one specific coefficient. So to get that coefficient, that is the part that's out in front of the, the term that has the x. And so we want to take the second derivative, 8x cubed plus 6x squared plus 4x plus 2. That's the first derivative. Then we're going to find the second derivative. And the second derivative would be 24x squared plus 12x plus 4. And then we're going to evaluate the second derivative at the place where it's centered. So this one's centered at 3. So then we put 3 in there for all the x's. So we got 24 times 3 squared plus 12 times 3 plus 4. And I think that comes out to 256. And then we're going to take 256 and we have to divide it by 2 factorial, which is going to give us our answer of 128. Number 10, here you have a geometric series. It doesn't really matter because we are finding a partial sum. So when it says this s sub 5, s sub 4, whatever number it says here, that's where we are going to stop. So we're not taking the whole sum of this infinite series. We're only taking the sum from n equals 1, and we're taking the partial sum to 5. So this question is asking, do you understand what this notation means to find s sub 5? This is a partial sum, and this is what we did on the first day of series, finding partial sums. We just stop at that point. We add up all the things before that. You can actually just type this into Desmos. Remember, if I'm typing into Desmos, I usually just use x instead of n. You could also use the calculator. So we want to say x is going from 1 to 5. And again, if you're doing this in Desmos, you're going to have parentheses around the top here, around the exponent, x minus 1. So when you type that in for number 10, you get a partial sum of 5.5462. So that is going to be your answer that you type in. It says round to the nearest thousandths, so that is 3 decimal places. If you go a little bit further, that is okay as well. Number 11, asking you to find the limit using the ratio test. So we're going to find the limit here of a sub n plus 1 over a sub n. And let's write this out. So we're going to take the limit as x, or I should say n again. N goes to infinity of the absolute value. We don't really need the absolute value. Now we got to put in n plus 1 wherever we see an n. So I'm going to put that in the top here. Then I'm going to put 6 to the n plus 1. And we're going to put 2 times 4. The 4 is being raised to the n plus 1. So everywhere that I see an n, I'm going to put in n plus 1. So this is the second, this is the next term, the n plus 1 term. And then we're going to divide by the previous one, which means we're going to multiply by the reciprocal. So we got to flip this guy. And we just write down the original, which is 2 times 4 to the n. On top, 8 minus n. On the bottom, 6 to the n. We'll simplify this. So this we can distribute 8, and then we're going to have negative n minus 1. That's going to be 7 minus n. And this is 6 to the n plus 1. This is 2 times 4 to the n plus 1. Over here we have 2 times 4 to the n plus 1, or just to the n, to the n. And then 8 minus n, 6 to the n. Okay, and when you're doing the ratio test, you're looking for things usually that have exponents to cancel out and things that have factorials that you can cancel out, and then take the limit after that. So The 2's here, we have a 2 on top and a 2 on the bottom, those can cancel out. And then we have 6 to the n plus 1 here, we have 6 to the n. So we have one more 6 on top. Here we have 4 to the n plus 1, here we have 4 to the n. So we can cancel out and we're still left with a 4 here. 6 over 4, we can reduce that to 3 halves. And now we have to worry about these two terms. But these two terms are both linear. They grow at the same rate. If you rewrite them, we can rewrite them as negative n plus 7. And over here it's negative n plus 8. And those are growing at the same rate. So we can take the limit as n goes to infinity. And basically negative n plus 7, negative n plus 8. That fraction is going to go towards 1 as n goes to infinity. So I'm just going to cancel those out as well. That fraction is going to go to 1. So what are we going to be left with is 3 on top and 2 on the bottom, which is going to be 3 halves. Number 12, this is probably the hardest one because you have to set up the integral and then you have to take the limit. Here we have the series going from n equals 1 to infinity of 2 to the negative n. And so we're going to take the integral going from 1 to infinity of 2 to the negative x dx. That's the integral. Now that you have the integral set up, we're going to have to take the antiderivative so that we can figure out what the limit is of that integral. And this is an exponential, but it doesn't have e as our base. It has 2 as our base. So you have to use the antiderivative rule of a to the x dx, or a to the u du. Okay, so if you go back to your integration rules, look up this one. Actually, it probably looks like this. And you'll find out that that is equal to a to the u over natural log of a in this case. This case is going to be 2. So that is the formula that you're going to have to use when it has a different base. So for this one, when we set it up, we take the antiderivative. The antiderivative of 2 to the negative x is going to be 2 to the negative x. Just like e to the x, it's e to the x. But since it doesn't have a base e here, we're going to divide it out by natural log of a. In this case, a is 2. And we also have to account for the chain rule here, taking du here. U would be negative x, so du would be negative dx. So we're going to have a negative sign out here as well when we take the antiderivative. So we have to evaluate this from 1 to b and taking the limit as b goes to infinity. So first off, we're going to evaluate this limit from the top, which is at b. So we're going to have negative 2. This is to the negative power, so we can put it on the bottom. So we're going to have negative 1 over 2 to the b, natural log of 2, minus, and then we subtract the limit on the bottom here. We're evaluated at the bottom. So that's another negative 1 over 2, because it's 2 to the negative 1. We're putting 1 in there for x, natural log of 2. So when we take this integral and then we evaluate it, this is an improper integral. So we're going to have to take the limit as n goes to infinity of this improper integral. The first one is going to be 2 to the b. We're taking the limit of this as b goes to infinity. And we can rewrite this. These two negative signs are going to come to be plus. So they have this term written first, and then this term is going to be written second. So our best answer here is this guy. Limits here should say b. I got to change that. Find the limit of the sequence. For this one, notice that this is a quadratic. This is a power into the second, basically. This is a factorial. So use your growth, ideas of growth and L'Hopital's rule and such. The top is going to grow much, much, much smaller than a factorial. So this is just a power. This is a factorial. The bottom is going to grow a lot faster. So when you have a small over a really, really big, it's going to tend towards 0. So this one should just be 0. Number 14 for the alternating series test. Okay, for the alternating series test, you could look at the test for convergence number 2 classwork and go to the alternating series remainder questions like 13 and 14. We're doing a similar thing here. We're going to find the remainder, which is going to be less than or equal to the next term. So if here we look at this, it has n cubed on the bottom and it's alternating. That's what the -1 here on the top raised to power is telling us. The least number of terms so that we get within 0.001. We're going to need that. So we're going to set this up as 1 over, we can use n here. I'm going to use x though, so you can type it in Desmos. So we're going to type in x plus 1. That's going to be the next term, raised to the third. And we want to find out, when is this less than or equal to 0.001? And if you're using Desmos, you could just plug it in. Otherwise, you can solve this algebraically. Just cross multiply and get to, eventually you have to take the cube root and then subtract 1. So when you do this, it should come out to 9. So the best answer for 14 is 9. Last but not least, number 15, the nth derivative of g is given by this function, and we want to find the coefficient containing x to the fourth in the Maclaurin series. So Maclaurin series means it's going to be centered at 0, so that's helpful. We need to get the fourth derivative, so we're going to put 4 in here for n. So we're going to have -1 raised to the 4. We're going to have 4 plus 5 factorial over 4 plus 6. And then after that, we're going to have to divide that whole thing by 4 factorial. So you just have to do this calculation and put it into Desmos or put it into your calculator. This one comes out to a whopping 1,512. So 1,512. So sometimes the numbers can get really big because, again, we're dealing with factorials. And if it comes out to a decimal, make sure you round to 3 decimal places. All right, so hopefully that helps. Let me know if you have any other questions, and you can send me some emails if you have any other questions on the quizzes or the test review. And we'll see you next time. Bye.